Okay, good morning and welcome to this webinar. My name is Joachim. I work at Noah Solution in Sweden, and today I have Christopher Seidel with me, who will present Mastering DevOps for Embedded System with ARM Innovations. So I just hand over to you, Christopher, and you can introduce yourself and get going.
Thank you, Joachim. My name is Christopher Seidel. I work for ARM in the tools business, let's put it that way. And I'm responsible for our tools such as Keil MDK. I look after SEMSys. And today, our topic is Mastering DevOps for Embedded Systems with ARM Innovations. I will talk about how our tools and services help you to run DevOps systems. So basically modern embedded development more easily. So this is our agenda for today. First, I will talk about how to improve the development flows. Then I will put more spotlight on the actual DevOps with continuous integration systems. I will also talk about MLOps, which is also a new field and very related to DevOps, just more specific to machine learning applications, which are coming more and more onto edge devices. I will show you one CI usage example, and finally we'll talk about our cloud native tools that we have available today. So before I talk about the improving the development flow, let's just take a quick look at the hardware that is designed by ARM. Here are some of the key innovations we've delivered to the market to satisfy the growing needs of the microcontroller market. In the early 2000s, we focused on enabling ultra low cost, low power, and small area applications for tiny sensor devices, which we provided with products such as the Cortex-M3 and the M0 Plus, for example. Later, we continued to drive performance too. So as security became more important in our world, we introduced the trust zone for Cortex-M, so ARM security, and which led to the introduction of the Cortex-M33 in 2016, which delivered another step change in security. And more recently, as the needs for more ML inference and DSP compute grew, we introduced the ARM Helium technology. And this makes it possible to deploy more compute-intensive ML inference algorithms in endpoints without a dedicated NPU, for example. And today, we extend those ML and DSP capabilities to the highly efficient space with a Cortex-M52, which we just released by the end of 2023. So this just as a quick look at how complexity and of course performance increased over the years. This is roughly a timeline of 20 years. So how can or do we have to improve the development flows for embedded IO and IoT? So for example, today we need a cloud storage service for our repository, and with cloud I mean off-prem or on-prem. So I would say also a server in your own network is kind of a cloud device. Of course, it depends on how good it is backed up and things like that. But typically, you have a repository hosting service that includes access control and collaboration features for distributed teams. And then for the software development environment, instead of installing an IDE or other software tools on your local device, you could set up access to the cloud service provider where you have something like software as a service. And I will talk about this at the end of the webinar. For continuous testing, a server running in the cloud contains a tool environment with simulation models and specific settings to your project. And when you deploy your software onto many devices, over-the-air programming offers methods to provision and update software of devices that are already in the field. And finally, once you have deployed to the field, you can use data analytics to monitor devices and spot anomalies, and, for example, collect training data for ML algorithms that can be deployed to IoT endpoints. So even in ML, this over-the-air update is important, as you can refine the models with all the data that you have collected. So how does that all work together in a typical application? Software standards and standardized development tool platforms reduce the overall product cost and improve quality. And so the IoT application usually sits on top of an RTOS that is using some network connectivity to talk to the cloud. An ML model might help in doing a specific task, so some kind of endpoint application. And when you use, for example, ARM's PSA APIs, you can interface to your secure firmware that might hold the required access keys for the cloud, for example. Below that, usually you have a layer of abstraction for the hardware, and having development tools that understand this layered concept using the standardized interfaces is really key to successfully create an application. And I come to that point later in my talk. Excuse me. Let's take a different view at the slide before. I hope you all have heard about CMSIS, the Common Microcontroller Software Interface Standard, which is a key industry initiative from ARM and our ecosystem partners that helps to standardize the way how we build embedded applications. Today, there are many different software components available that help to use our cores and specific architectural features, such as DSP or neural network engines, for example, our our Ethos-U NPUs. But there are also tools available that optimize development flows. So one of them, for example, is CMSlS-Pack down here, which is a delivery mechanism for device and board support, as well as software components. And here we also have the CMSIS Toolbox and CMSIS Stream, which are building blocks that make debugging more efficient and less time consuming. And let's talk about what's new in CMSIS 6, because we have just released that version also at the end of last year. Was kind of a very nice Christmas present. In CMSIS 6, we have new components such as CMSIS View and CMSIS Compiler, basically the CMSIS Toolbox and CMSIS Stream. And these new components, we are currently running a webinar series where we are explaining these components in more detail. Just let me quickly add that CMSIS View adds new debug capabilities with event recorder and component viewer technologies. Basically, they are using low overhead code annotations that do not require any sophisticated debug functionality. So they basically work with any debugger. The CMSIS compiler, the CMSIS compiler helps to retarget I/O functions of the standard C runtime library. And we have written it in a way that it is compiler agnostic and works with all major tool chains. So GCC, ARM compiler, LLVM, and also IAR. The CMSIS Toolbox is a set of command line tools that work with CMSIS packs and enable reproducible builds on the command line or using a GUI. Again, I will talk about that in more depth later. CMSIS Stream is a Python package that provides methods, interfaces, and tools to optimize data block streaming between processing steps of a DSP and ML application. So this is already quite a kind of a niche block here, but it's very important for these new types of application. We have also optimized the structure of CMSIS. So the ARM CMSIS pack today only includes the CMSIS core and the APIs that are available through CMSIS. Other components such as DSP, for example, or CMSIS NN, they are now available through separate repositories for better maintenance and faster release cadences. We usually release a CMSIS update twice a year But our colleagues who are doing the DSP, for example, they are much, much faster. So that's the reason why we have taken that out. So much for SAMSys. Now let's talk about DevOps with cloud-based continuous integration. And basically, before we jump into that topic, what is test-driven development, DevOps, and CI/CD? Some of you who are not using that already might have heard some of these words, but maybe cannot really think about what is behind that. So test-driven development embraces the fact that software requirements are converted to test cases before the software is fully developed. So you kind of do test first before you write the actual code. So you write already the test cases based on the requirements. DevOps helps you to shorten the system development time by providing continuous integration, test, and delivery. This is this nice circle here on the right. Yeah, so you are going through these circles with DevOps, and basically the ops part, the operations part, is the CI/CD part, and this integrates incremental code changes from several developers into production code when they push, for example, to a GitHub repo. You run automated tests to verify the functionality. You deploy firmware images to test fleets. And of course, you can do the large-scale delivery to many endpoint devices with that. As you can see, testing is very important. I hope you all know that. And yeah, this is another representation of the V model. I think we all know and love this model. And I want to just pick a couple of blocks here. So especially, for example, the unit testing part, which actually tests little chunks of code at a time, and they are usually tested against your test build. And then we have the integration testing, where you test whether two components work together as expected when they are combined. It verifies that the interfaces are working properly between these components, and it's also tested against the test build. And when we move up the ladder here and jump over verification, and we are talking about the system or black box testing, then this is to test if the final system works as expected. You use external controls and stimuli to the system to measure the response. And this is usually done against your release build. So when you have removed all the debugging or whatever. And one thing that is not really here, but it's kind of this circle, is the regression testing. So this is a suite of tests, unit and integration tests that run continuously upon version control updates. And this is used in continuous integration. And this little graphic here on the right shows that setting up CI comes at a cost. So you have usually in the beginning a steep learning curve that you have to climb. But in the end, you will be happy because the overall effort is much less than if you do no CI. The more complex your application gets, traditional test methods or traditional setups tend to just shoot over the roof with the effort. So using a CI and a CD system has really lots of benefits. One thing where we start to talk about the innovations that ARM is providing is why do we have problems with hardware-based testing? And mainly 3 points that I see here. The first is the scalability. Adding more hardware is not really a linear effort and can be a bottleneck for developers if you cannot submit your test code to a hardware board because all of your boards are currently used by other developers or whatever, then this becomes a problem. The overall complexity is very high. Board farms can become really expensive. They are not standardized, so everybody has to roll their own. and they introduce high engineering costs. And finally, stimulating the IOs is possible to some extent, but additional infrastructure complexity is needed here, and maybe not all test cases can be reproduced consistently. So this is what we see with hardware-based CI/CD testing, and this is the reason why we have come up with this modern development DevOps workflow. And here on GitHub, we have an example repository that is using this flow. So how does this work? On the left side, we have our traditional developer who is sitting in front of his machine, and he submits his code to a code repository. And once the code is in this repository, the CI pipeline kicks off. So the code is built, then it is tested, and the results are then basically fed back into the code repository, and the user can check the CI results. This is the magic part. The testing. The testing is not really. We propose not to run it always on hardware. Hardware is only kind of the final step, but in between, when you do little code changes, little updates, run all these unit and integration tests, you should think about ARM virtual hardware, which is a cloud. So we have it available as a cloud service. We have them also available as part of Keil MDK, as executables that you can run locally on your machine. That's why we have this local development bubble here as well that can also access ARM virtual hardware. And what ARM virtual hardware is, I will tell you in the next slide. Maybe one final thing. Of course, if you run the local development loop, then you can have access to some development hardware that you have on your desk and can do, of course, complex debugging. Sometimes, let's say, if in the CI pipeline you see a problem, then you need to run this local loop and do the complex debugging to find the root cause of the problem. So this is what we see as a modern development ops workflow. And ARM virtual hardware, let's talk about that more in detail. So what is ARM virtual hardware? Basically, it's precise simulation models of a Cortex-M device and its subsystems, which are specifically designed for complex software verification and testing. You can run basically any code on it, RTOS code, bare metal code, whatever. It doesn't care. And the nice thing about it today is that it provides virtual peripheral interfaces for I/O simulation. For example, Ethernet, UART, GPIOs. And that basically enables test automation of diverse software workloads, including unit and integration tests and fault injection. Fault injection is a big problem for hardware. Think about motor control. If you are running a motor control algorithm and the motor is running at high speed, lots of RPMs, you don't really want to inject a fault in there, because that can have very diverse problems up until the motor goes up in flames or whatever. So this can be kind of mitigated when using ARM virtual hardware, where you can insert such faults. And as ARM virtual hardware is either kind of an on-prem thing that you can run on your server or in the cloud, it can be very easily integrated in DevOps and MLOps workflows. So how can you, for example, test a cloud application with internet connectivity? This is a kind of a complex block diagram, but in the end, it's quite easy. Here on the top, you have your application that is, for example, using SEMSys RTOS 2 API with, for example, FreeRTOS. You can incorporate our new technology, the event recorder, which is part of SEMSys View, as I was talking before. And we have some demo test interfaces. For example, the application is a voice recognition. And of course, it needs a TCP/IP networking stack. And in between, we have the layer of virtual interfaces. So for example, SEMSys VIO for virtual IOs, an audio driver for the virtual streaming interface, and an Ethernet driver. And in the end, we have the virtual target, so the ARM virtual hardware, where you can capture the event recorder data. You can run a demo interface, virtual streaming interface to stream audio data in and out. And we also have a virtual socket interface. So how this works for the virtual stuff is basically you are using a BSD socket, and that can connect to the virtual socket of the virtual hardware interface, and then connect to the cloud, basically using the internet connectivity either of the server where you are running the model on, or your local PC if you run the model locally. And yeah, down here you see you can have events on changes of LEDs. We have a Python interface to script the audio input and output. And yeah, the connection to the internet is via the socket of your local machine. So this is how you can test your user application on virtual hardware, behaving very, very similar to real hardware. And if we think about an ideal flow, for example, you start on the left-hand side with unit integration testing on virtual hardware or physical hardware boards. So here on the left is what I explained before. You're using virtual layer, virtual drivers, and then once you move up the ladder, kind of, you can use a board layer with hardware drivers and SDK with configuration on a off-the-shelf development board, yeah, where you can then also do real I/O with test equipment. And once your hardware department has created your custom hardware, the one that you really want to ship to your end customers, then you just need a different target layer with, of course, the hardware drivers for the target, maybe some additional drivers, SDK configuration, and you can also run this real I/O via the user peripherals. Using event recorder, so SEMSys View, for debugging purposes, so checking how your code behaves, is very advantageous in this flow here, because at any point in time you can write out event log files and compare them against each other. So you can really find out how well your code behaves, and essentially the same logs are generated across the different deployments. I mentioned the SEMSys toolbox before. So how can we basically achieve this development flow? And in a joint effort with NXP and ST Microelectronics, we were specifying a new way of creating projects across different tool chains. And we call this the SEMSys toolbox. It basically consists of all the tools you need to work with SEMSys packs. SEMSys packs, as I said before, is the delivery method for boards and devices, so board support and device support, as well as software components. And for example, one part of the SEMSys toolbox is a small tool called CPack Get that helps you to download packs automatically that are not available on your machine. And the main tool is called C-Solution that manages the whole project and helps to create software, create complex solutions for your application. So you may have different contexts, and these contexts may be unit and integration tests on AVH simulation models, where the virtual drivers implement the interface to the simulated I/O. Then you have another context, which is the unit and integration test on real board with hardware I/Os, or another context where you do the system tests, where the software is combined with more or other software components that compose the final application. So overall, the SEMSys toolbox ensures reproducible builds throughout the whole product lifecycle management. And it's based on very simple YAML files. And for example, you see we have here the different targets, virtual target, the board, which would be kind of a normal development board, and the actual hardware that you're using. We have different build types, release and debug. And then we have, for example, here's a multi-project application where you have the actual user application, and then maybe, for example, a trusted firmware to run security. With the SAMSys toolbox, we have also changed the way how we deliver our tools to users. To accommodate these requirements of CI/CD systems, you can now download the tools separately without the need for a login. Previously, you had to go, for example, to keil.com and download MDK version 5, and then you need to run a graphical installer where you need to click through and whatever. This is, of course, way too complicated for CI/CD systems. So now these automated systems can download, install, and use the tools as they require. And we are using, under the hood, the technology is called VC Package from Microsoft. This is a package manager from Microsoft that works on all major host operating systems. So it enables Linux, Windows, and Mac OS systems. And it's basically using a configuration file in JSON format that tells the package manager which tools to download from which location. And this ensures consistent tool setup that can be reproduced, for example, in 5 years' time, when you need to fix a bug that happened in the field and you need to recreate your whole development environment with the SAMSys toolbox. And this way of delivering tools, it's really easy. And on GitHub, we have another repository that shows this, how to use this in an MLOps environment. Talking about MLOps, this is, I will now maybe a little bit turn into the MLOps development flow, highlight the differences to, let's say, a standard DevOps flow. So MLOps is basically the art of deploying and maintaining machine learning models. And so you combine the machine learning data analytics with continuous development. And usually machine learning models, which in the end are algorithms, are tested and developed in isolated systems where you then process the data and you create your model. So MLOps is basically a process between data scientists, DevOps, and machine learning engineers to transition the model to a production system. And MLOps applies to the whole product lifecycle, and as you can see here is an iterative process. And many embedded systems introduce ML technology in kind of an evolutionary process where you start with first a classical decision algorithm for data collection and then later go on to a MLOps model or ML model. And the model evaluation and the system validation requires that the ML model is executed with the final instruction set and capabilities. And this is where we again talk about ARM virtual hardware and the so-called SDS framework I will touch on in the next slides. And so what happens when you don't train your model correctly? Correct decisions can only be made in areas where training data exists. And learning in the machine learning way means that ML algorithms are retrained based on new experience. So as your devices are in the field and maybe collect data from the field, you can retrain your models to make them finer. So here's a funny example. This picture, if the model is not trained correctly, it could say that for us, very obviously a picture of a cat, but it can be a bath towel, I think, because it's lots of white stuff in here, and maybe a paper towel, but not a cat. So it really, if you have these blind spots here with no training data or not good enough training data, then such things can happen. So how can you train your model? And here we come to the SDS, the synchronous data streaming framework. So this is basically one of the big problems, to record and replay the training data, especially when you want to replay the data on virtual hardware. need means to record it first. And for that, we came up with SDS. So SDS allows you to record and play back real-world data for analysis and development. And you can use this data, for example, with filter designers as an input for your ML algorithm development. So what is happening here? We have a real-life microcontroller device with, for example, a gyro and a microphone input, and we feed this this data through the MEMS sensor device and the audio device to the algorithm under development. But at the same time, we are recording this data with this SDS recorder interface. And this interface can connect to different channels. So for each of these channels, for the gyro, for the microphone, for whatever, you get different SDS data files. So gyroscope SDS and microphone SDS. And you can, these data are now available in kind of machine readable format, and you can convert this to the ML training platform to be automated. So you get a nice training data that you can use to run your ML model, or you can also use this as test data wherever you want to do that. And once you cross over to the simulation, to the virtual hardware, you can basically feed in these SDS data files via virtual streaming interfaces into the AVH and run your tests on it. So this enables repeatable test automation in MLOps services. And yeah, it's a flexible stream management for sensor and audio data. It supports the whole development cycle, data recording, analysis, ML training, playback. And important thing is that sensors may have independent clock sources with tolerances, and thus SDS is capable of handling sensor fusion with clock deviations. And Python utilities allow recording, playback, visualization. So these plots here are using standard off-the-shelf Python tools, data conversion, algorithm verification with offline tools. And basically we have the recorded files, and then we have a so-called metadata file, which is a YAML-based file, human-friendly, easy to read and write, which tells the tools what is actually in that SDS data file. How can you use that in MLOps? We have basically teamed up with our partner Keil, a company just recently bought by TDK, to test this whole flow. And this is how they use it in their flow. First, of course, they capture the data, so they have added the SDS framework to their target application. They capture the data files. They verify that the SDS data files are correct using a viewer, and then they convert these data files in an import step and label the data. Of course, ML lives on correctly labeled data. And then they use that in their MLOps system called Keil AutoML. They do the model training with this data, feature extraction, model selection, everything you need in a good ML flow. And then they deploy it to a target, and they validate it on ARM virtual hardware, and of course also final system tests in target hardware. So this is already available with Keil AutoML. We are working with other ML partners to provide a similar service soon. And I have brought one CI usage example with me. So this is, for example, how to verify complex application. So imagine you want to create a smart speaker that has a digital microphone array for the commands issued by the user and an audio front end. And there's lots of traditional signal processing to the task. And then, of course, there's the ML part to detect the keywords. And using all the tools that I've shown before, you can verify the correctness of your algorithms and also compare different algorithms. Yeah, and the question is how. We have a repo for LVH that is doing this. This is a TensorFlow microspeech example. And using the virtual streaming interface, you can stream pre-recorded data into the AVH and thus test the behavior. And the audio driver supports multiple channels and data formats. And the data then is transferred in blocks each after each. So you see this audio buffer handling is in block, and a callback event is triggered for each block, and thus you can mimic the actual audio input into a real device. What we're also using here is the SEMSys View, again, event recorder ARM component viewer. And with SEMSys View, you can annotate your code to gather usage statistics and to compare different implementations. So this is using some of the built-in features of the models. It's not 100% accurate, so it's not really like you cannot tell the absolute performance of a model, but they are functionally accurate, and you can, for example, compare different implementations against each other. So let's say you have created your code and your application in the first shot, and then you see how it behaves, and then you tweak it a little bit, you rerun the tests and check the event recorder log data, and then you can compare these two implementations against each other and see which one is better. And so it's really giving a good indication regarding the performance, and we are using this technology in our code that is running on the Ethos U NPUs. And yeah, it's now available open source under SEMSys View. One tiny caveat, or let's say one thing you have to pay for is this event recorder technology is using a small amount of your RAM, where basically the event recorder data is written into this RAM, and the debugger continuously reads that RAM and transfers the data to your debugger. How, and this is how we can process the data. So again, you can also run comparisons between microcontroller hardware and ARM virtual hardware. So you're using the event recorder. In case of ARM virtual hardware, you can write directly a so-called CTF file. It's common trace format. And if you're using real hardware, you need, of course, a debug adapter with the debugger to write the CTF file. And then we have an open source tool called Event List. It's a command line utility that basically translates this CTF format into human readable format, which then looks something like this. So again, this is also an CI MLOps example that is available under this GitHub link here. We are using that in nightly build tests of for example, this MLOps example, and then you can see the event counts and total min-max average time, whatever. In different stages, it's depending on how you annotate your code. Coming to my, I think, final section for today, talking about the cloud native tools from ARM, and yeah, these cloud native tools, or how do we envision a flow for developers. Basically, we have a website where you can discover your possibilities, checking, for example, you got a latest and greatest development board at the Next Embedded World trade show or whatever trade show, or from your distributor, and you can check this website what kind of examples are available for that development board. You can import them directly into our cloud native tool, ARM Keil Studio, which is just running in your web browser. And once you develop further your application, you can move that to either our Keil Studio, which is running on the desktop in a Visual Studio Code environment, or in our traditional Microvision. And finally, of course, you deploy this to your custom hardware, and you can do further checks, more in-depth debugging, and whatnot. So this is the vision. How do we achieve that? We have, as I said, keil.arm.com. You have a search service for device and boards. You can discover the various example projects. We have a tab here for projects, and then you can directly download, for example, to download onto your computer, or you can open it in Keil Studio Cloud or whatnot. We have links to documentation, user guides, and feature sets. So this is a one-stop service to work with hardware. We also have a service here to detect hardware that is connected to your PC. Maybe one important point, because we are using web USB technology, we can connect to a target from your web browser, and this comes in very handy for Keil Studio Cloud. As I said, this is a browser-based development environment running in your browser. You don't need to install anything. You can use it freely. It also offers an ARM virtual hardware service. And you can connect via the web browser, via web USB technology to your target connected to the PC. So you can do simple run-stop debugging with it, even from within the browser. And this is basically the cloud native tool. And once you are, you need more, you can export that project, import it into locally installed development tools, and you can continue with, let's say, more serious debugging. And this brings me to my summary. Developing in a cloud native world, cloud native tools are here to reduce your time to market, improve the code quality. Most important point, don't be afraid of the cloud, and don't think that your IT department is much more clever than the IT department of people like GitHub or Microsoft or whatever. Yes, we all hear of breaches into big services, and this can happen, but we don't hear, because of the weight, breach into smaller companies, which happen every day, multiple times. So I know people are afraid sometimes of using the cloud because they say, no, it's not my data. It's still your data, obviously. And I believe that the protection of this data is much better on a big service than with a much smaller IT department. The other thing is you don't have to switch everything at once. Starting the journey is key. Yeah, so get started, take a look, maybe start with the browser-based IDE and play around with it, and then think about how you can move that over. And of course, we and our ecosystem support you with joint initiatives and common standards. And to start your journey, I have a couple of pointers here where to go next. keil.arm.com. We have multiple examples on GitHub, SEMSys6, MLOps, and the SDS framework. And with that, I'd say, Joachim, we're now open for questions.
Yes, thank you. I think it was very interesting contents that you presented to us today. So I think if you have questions, just run it in the chat, and we will answer them. I think also that we should mention that, as you mentioned, there is a seminar series of SEMSys6, and there have been 2 sessions already, and there are 2 more sessions, and you can reach that link to know our homepage under events and webinars. So I think that will be recorded as well, I guess. So it's a good entry point to start things. And we at Know How, we can of course help you if you need help to set this up and so on as a service. So no problem in doing that.
So we have the first questions.
Yeah.
How does this virtual hardware layer work when you have custom chips that are ARM IP but not actual ARM chips? So the ARM virtual hardware only simulates basically the core and its peripherals. So a Cortex M33, an M7, and an M0 plus whatever. So it does not really matter if it's not an ARM chip, as long as it's using one of the cores. You can do the simulation, and this kind of also answers the next one: which device families are supported by virtualization? So the complete Cortex M family, Of course, we have also models for Cortex-A class cores, but that's not where I'm coming from. So I'm the microcontroller guy. I'm more targeted towards the Cortex-M, and then we have, as I think I mentioned it, we have also the subsystems. They are then called Corestone. So an M33 with some additional building blocks and stuff like that. That's also available as a simulation model. Is ARM virtual hardware certified for safety critical software development, or are there plans to have it certified? The models are not certified for safety critical software development. We have our ARM compiler for functional safety that is qualified for FUSA. We have a software package that is available for FUSA, so our Keil RTX, together with the event recorder technology, and the ARM-specific SIMSYS core part is also available as for FUSA. The models themselves are not. But yeah, I mean, using the models would not harm. It would give you additional confidence in your software. And we are, for example, using the models to certify our function safety runtime system, so the Keil RTX part and whatever. And this is accepted by our certification body, TÜV.
I can also add that we at know-how, we have also tools like unit testing tools and static analysis tool that can be put into this pipeline thinking. So you can do some testing first on virtual hardware and then do certified testing on the target as well, if that is required by the standard.
Any other questions? Do the models run in real time, or can they be simulated at a faster rate? They're actually slower. Are they slower? So you can play around with clock frequencies and whatnot. I mean, the simulation should be slower than real time. But usually that's the nature of simulation. It depends, of course, also on what kind of machine you are using, how powerful the machine is, and so on and so on. There's lots of different influence to answer that question. It's not really easy. Does the SIMSYS View tool also run on Linux? So once again, SIMSYS View is not a tool. SIMSYS View is a software component that you can use in your application to annotate your code. And this event list tool that I was talking about, this runs also on Linux. And I mean, we are using Linux-based servers in the cloud to run our ABH testing and whatnot. So yes, it's written in Go. It runs on Linux, macOS, and Windows the like. So no problem. We are in general. I mean, I'm the MDK guy, and you may know MDK Microvision is a Windows only tool. It's quite an old tool. That's the reason why it's Windows only. And we are now going much kind of open is maybe the wrong word here. It's not open source thing, but we are now moving over to support all major host operating systems, Linux, macOS, and Windows. Our next generation IDE is Keil Studio, which is based on VS Code, which runs on all platforms. It's a set of extensions. ARM compiler is available in all flavors for x86, for ARM64, for Darwin, for whatever. So we are broadening the tools landscape because we don't want to mandate what kind of operating system you are running on. It's none of our business, it's your business. So you do the decision, and then you can use our tools wherever you like.
Okay. I think we are on time. I think if we include the question at least. So thank you very much, Christopher.
You're welcome.
We will send an email to you, all the attendees, with a link and a PDF format of the presentation as well. So thank you very much, and welcome to our next webinars in the future. Thank you.
Thank you for listening, and have a great day.
Thank you.
Bye.